Have you ever dropped a rock into a pond? It goes straight to the bottom, right? But then you see a gigantic ship, made of heavy metal, just chilling on the water for days, weeks, even months. It feels like some kind of magic trick. How can something so huge and heavy stay up, while a tiny rock sinks like, well, a rock? To solve this mystery, we're going to think like scientists. We'll observe, we'll make some guesses, and we'll figure out what really makes sense. Let's start with our first guess. Maybe ships float because they're made of a special floating metal. But wait, that can't be right. Most ships are built from steel, and if you drop a solid chunk of steel into the water, it sinks immediately. So, it's not the material itself. Okay, how about a second guess? Maybe ships are actually lighter than rocks. But that's definitely not true. A single anchor from a large ship weighs more than a car. The entire ship weighs thousands of tons. So, the secret isn't just about being light. Here's the real clue, the key to unlocking this whole thing. Floating isn't about how much an object weighs. It's about how much water that object pushes out of the way. Think of the water in a lake or ocean like a strong, invisible helper. When you place something in the water, it takes up space. That space used to be filled with water, so the object has to push that water aside. Scientists have a cool word for this: displacement. The object displaces the water, meaning it moves it out of its place. And here's where the magic happens. When you push water out of the way, the water pushes back. It doesn't just push from the sides, it pushes upward. This upward push is a real, powerful force that can hold things up. We call this force buoyancy. Buoyancy is a float force. So, the big question now is, how strong is this upward push from the water? The answer is beautifully simple. The more water your object displaces, the stronger the upward push, the stronger the buoyancy. A big displacement gives you a big buoyant force. A small displacement gives you a small one. Let's test this idea with something you might have at home, a piece of clay. If you take a lump of clay and roll it into a tight, dense ball and drop it in water, what happens? It sinks. The clay is heavy, sure, but that's not the whole story. As a tight ball, the clay doesn't take up much space. It's packed and tight. So, it only displaces a little bit of water. The upward push from the water isn't strong enough to hold up the clay's weight. But now, let's take that exact same piece of clay. We're not adding anything or taking anything away. We're just going to change its shape. Let's flatten it out. Mold it into a wide, hollow bowl shape, like a tiny boat. Now, gently place it on the water. Suddenly, it floats. It's the same clay, the same weight. Nothing magical was added. All we did was change the shape. The bowl shape takes up much more space on the water's surface. It pushes a lot more water out of the way. Because it displaces more water, the water pushes back up with a much stronger force. That's our first big lesson. Shape is a game changer when it comes to floating. Now, let's connect this back to our giant ship. A ship isn't a solid block of metal. If it were, it would sink just like that steel chunk we talked about. Instead, a ship is mostly empty space inside. It's designed like a massive, hollow bowl. The bottom and sides of the ship, called the hull, are shaped to hold a huge volume of air. This air is what allows the ship to take up an enormous amount of space without being a solid, heavy lump. So, when a ship is launched into the water, its huge, hollow shape displaces a massive amount of water. Massive displacement means a massive upward push from the water, massive buoyancy. The water pushes up with enough force to perfectly balance the ship's enormous weight, and that's why it floats. The secret isn't that the metal is special, it's that the shape is special. It's wide and hollow for a reason. Let's revisit our little rock. Why does it sink so easily? A rock is dense. That's a scientific way of saying it has a lot of stuff, a lot of matter, packed into a very small space. When you drop that rock into water, it only displaces a tiny bit of water because it's so small and solid. So, the upward push from the water is also tiny. The rock's weight is much, much greater than the water's upward push, so down it goes. This leads us to a super simple rule you can use for almost anything. If the upward buoyant force from the water is stronger than the object's weight, the object floats. If the object's weight is stronger than the upward buoyant force, the object sinks. That's the fundamental principle. Now, we can get a little more technical and use that word scientists love, density. Density is just a measure of how much stuff is packed into a certain amount of space. Things that are very dense, like rocks and solid metal, usually sink in water. Things that are less dense than water, like wood or a plastic bottle full of air, usually float. But here's the fun twist. A very heavy object can still float if its average density is low. A ship is incredibly heavy, but because it's filled with so much empty airspace, its average density, the total weight of the metal and everything inside, divided by the total space it takes up, is actually less than the density of water. That's the genius of its design. It's how the same metal can sink as a solid block, but float as a majestic ship. Think about another example, a life jacket. A life jacket isn't made of heavy metal. It's made of foam filled with thousands of tiny air pockets. Those air pockets make the life jacket take up a lot of space without adding much weight. When you wear it in the water, it displaces a lot of water relative to its weight. The water pushes up strongly, and that buoyant force is what helps keep your head above the surface. A life jacket is basically a tiny, wearable ship. So what happens if you load a ship with too much cargo? As you add more cargo, you add more weight. To stay afloat, the ship needs to get more upward push from the water. To do that, it has to displace more water, which means it has to sink lower into the water. Every ship has a line on its side, called the plimsoll line, that shows the maximum depth it can safely sink to when loaded. If you load it beyond that point, it sinks to low. Water could start splashing over the deck and getting inside. If enough water gets inside, the ship starts to lose that precious hollow space filled with air. It can no longer displace enough water to counteract its own weight. The upward push becomes weaker than the downward pull of gravity, and that's one of the ways a ship can tragically sink. So, the ship's real superpower isn't its weight or its metal. It's its ability to maintain a large, hollow shape that displaces a massive volume of water. Let's close the case. A rock sinks because it's dense and solid, so it only displaces a little water for its weight. A ship floats because it's hollow, allowing it to displace a huge amount of water, which generates a powerful upward buoyant force to support its weight. The mystery is solved. And now for a little scientist challenge for you. Find 3 common objects around your house: a coin, a plastic bottle cap, and a metal spoon. Before you put them in a bowl of water, make a prediction. Which ones will sink and which ones will float? Then, test them out. Think about why they did what they did. Which one displaced the most water for its weight? And here's a bonus challenge. For anything that sinks, like the spoon, can you think of a way to change its shape or combine it with something else to make it float? Because that's what science is all about, understanding the rules so you can change the outcome. In the world of floating, that rule is all about shape and displacement. That's the secret behind every boat, every ship, and the incredible, surprising strength of water. Thanks for watching, and remember to keep asking questions. See you next time.